begin our final session. So this strongest features of the life. So and the speaker will be Spiro Karigiannis. So he will tell us about G2 conifolds.
Okay, thank you for the introduction. Good morning, and I want to thank everybody who was brave enough to avoid fleeing early from the dire weather predictions, and who also got up early enough to come here on a Sunday morning. I also want to say on a personal note, 10 years ago I was still a graduate student, and I was at Blaine's 60th in the other building. And I remember being truly in awe of all the depth of the mathematics that surrounds Blaine. So it's really a great honor for me to be able to participate 10 years later and tell you something about my work, which again is definitely closely connected to lots of things you've been hearing all week, and to the work of especially Harvey and Lawson. Okay, so I'm going to do something a little ambitious. I'm going to talk about things that are in 3 separate papers. One is on my own that was published 4 years ago. Another one is work with Jason, who's somewhere over there, which should be on the archive in a week or two. And then this other work with Dominic Joyce, which is going to take me a while to tech up, so probably next year. Now, this normally would be crazy to try to do this, but I think in this, if I can do it anywhere, I can do it in this audience, especially since I've had Conan and Mark and Sema tell you a lot about G2 manifolds already. So the first few slides will be a bit of a review with my own point of view on it. But definitely interrupt me if you have questions, and I'd much rather just tell you about 2 of those things and have you understand than try to do all 3 with no success. Okay, and the last thing before we get started is, Mark made a big deal about how Conan was wrong in using capital omega for the 3 form, and he's definitely correct. You're definitely correct about that. Omega is a crazy choice. But Mark and Sema are also wrong. It's not phi, it's var phi that Blaine and Reese used in their paper. So I will always use var phi for the 3 form. Okay, so again, let me start with a brief review about G2 manifolds. Some things you've heard already this week and some things you haven't. So we have a smooth 7 manifold. A G2 structure on the 7 manifold for topologists is the reduction of the structure group of the frame bundle from GL7 to G2. And you can view G2 explicitly as a subgroup of SO7. So these structures come with a metric and an orientation. And this has already been mentioned, such a thing exists if and only if the manifold is orientable in spin, the vanishing of the first 2 Stiefel-Whitney classes. So there are lots of manifolds with G2 structure. And the way to encode this for differential geometers is there's a 3 form, a smooth 3 form, which is non-degenerate in some sense, which I'll explain probably on the next slide or sometime very soon. And this 3 form, from this 3 form, it induces, it determines a metric, a Riemannian metric, and an orientation in a very nonlinear way. And therefore, we get a Hodge star operator, and we have a dual 4 form, which I usually write psi. And again, this has been mentioned already. If you have a manifold G2 structure, one way to think about it is that each tangent space, each 7-dimensional inner product space has the structure of the imaginary octonions with the cross product and all that. But nothing new here. And then if we have a manifold with G2 structure, we get a metric, a Levi-Civita connection. We say that it's a G2 manifold if the 3 form is parallel. Again, let me use the pointer there. That's a nonlinear equation on phi because nabla is determined from G, which is determined nonlinearly from phi. And I will definitely call these torsion-free G2 structures where T nabla phi is the torsion. Actually, I noticed during the week everyone was using the right board for the pointer, and I kept getting lost because I was looking at the left board. So I'm going to try to change it up and keep you on your toes. Okay, so why are these important, or why are they interesting? If you have a G2 manifold, then the holonomy is contained in G2. It may be a proper subgroup. And if it is equal to G2, I will call these irreducible G2 manifolds. And Mark already mentioned this, that once you know the holonomy is contained in G2, whether or not it's equal to is just a topological question, if and only if the fundamental group is finite. If M is compact, yeah. And the metric is Ricci-flat for these. So they're examples of Einstein manifolds. And they admit a parallel spinner, which is why they're interesting in physics, because physicists keep telling me that parallel spinners equals supersymmetry, and that's almost all the physics I know. I used to know more, I think, and I've forgotten. So they play the role in M theory that Calabi-Yau's play in string theory. And an important result is that a G2 structure is torsion-free, that is, it's parallel, if and only if the form is closed and co-closed. So one direction, of course, is trivial. Any parallel form is always closed and co-closed. But to go the other way is the non-trivial part of this. And this uses representation theory. So it uses the algebra of the octonions in a very deep way. So this is Fernandez and Gray, 1982. And both the 3-form and the 4-form are calibrations. So they have families of calibrated submanifolds, associative and co-associative submanifolds. Okay, I want to say a little bit about comparing G2 geometry with Kähler and Calabi-Yau geometry, because there's some similarities and then there's some very important differences. So they both have calibrated submanifolds. We heard a lot about that this week. They also both have calibrated connections. So for example, the Hermitian-Einstein or Hermitian-Yang-Mills connections. Anyway, I don't want to say too much about the connections, but there's the Donaldson-Thomas connections too that we heard about earlier in the week. And they both have Dolbeault-type decompositions of their cohomology, which implies restrictions on the topology. Again, let's just restrict to the compact case. So there's a lot of things that are in parallel that are analogous. But of course, not all Kähler manifolds are Ricci-flat. The ones that are Ricci-flat are the Calabi-Yaus. And we know exactly which compact Kähler manifolds can be Ricci-flat, and that's the Calabi-Yau theorem. That's C1 equal to 0, again in the compact case. And we're very, very far from knowing the same conditions for existence of a torsion-free G2 structure. Really, the question is more analogous. The question is more analogous to saying, suppose you have an even-dimensional manifold that admits almost complex structures. What is a sufficient condition for it to admit Kähler structures? And we're very far from knowing the answer to that. So in some ways, they're more like Calabi-Yaus, because they have the parallel spinor and the Ricci-flatness. In some ways, they're really more like Kähler. Okay, and I want to emphasize the G2 geometry is quite a bit more nonlinear than Kähler geometry, because in Kähler geometry we have this DD bar lemma, which is a fantastic tool for simplifying differential equations. The DD bar lemma, you use it repeatedly to reduce a first-order system of PDEs to a single scalar equation. So for example, the Calabi conjecture can be reduced to a fully nonlinear Monge-Ampère equation, but a single equation for one function. But the natural PDEs which arise in G2 geometry and in all other calibrated geometries, except special Lagrangian, are usually first-order, fully nonlinear systems. Okay? So you can't reduce it to a single function, and it's harder to deal with. And again, I think Sema mentioned this yesterday. In Kähler geometry, the Kähler form and the complex structure are essentially independent. There's this mild condition of compatibility, which is easy to arrange. And then once you have the two, they determine the metric G. So you can think of Kähler geometry as being complex geometry and symplectic geometry put together, and they're almost independent. But this does not happen in G2 geometry. Again, this has been mentioned this week. And it's because the 3-form determines everything else from this formula. There's a constant here that depends on your conventions. So the left-hand side only has the 3-form in it, and the right-hand side has the metric and the volume form. And since you know that it's a 7-dimensional manifold, from this formula, you can actually extract separately the orientation and the metric, and you can get everything from the 3-form. So, and this, if you want, you can take this as a definition for non-degeneracy. If you have a 3-form on a 7 manifold, and this formula actually produces a G which is positive definite, then you can say the 3-form is non-degenerate. And you can see right away that it's an open condition. So the punchline is we can't decouple G2 geometry into two separate geometries and try to make one as nice as we want first and then try to improve the other one, like we do in Calabi-Yau. Okay, so all this was supposed to be review. Let me say something about examples. First, we're going to talk about the complete non-compact examples. So the first ones were found by Robert, who's already gone, and Simon Salomon in 1989, or maybe it was 87. So these examples are non-compact. The manifolds are total spaces of vector bundles, and it's these three in particular. These are two rank 3 vector bundles over 4 manifolds, and that's a rank 4 vector bundle over 3 manifold. That's the spinor bundle of S3. So, I mean, these are important because they were the first complete examples of irreducible G2 manifolds. From now on, if I say G2 manifold, I will always mean irreducible. And the important thing about these is that they're asymptotically conical. So I'm going to define asymptotically conical in a few slides. And when I do, I will remind you that these three are examples of asymptotically conical. So that means that if you look far away from the base, near infinity, these are non-compact manifolds, they kind of look like a metric cone in some way, which I'll make precise. And since then, there's lots of other complete explicit examples on non-compact manifolds with nice asymptotic behavior at infinity, like asymptotically cylindrical or asymptotically locally conical or things like that. Most of these are found by physicists. There's a whole industry of finding these things, and I can't keep up with all the examples. But I think almost all of them, and possibly all of them, are cohomogeneity 1 G2 metrics. That means they assume that there's a certain group acting on the manifold that preserves the structure with, well, there's a group acting with orbits of cohomogeneity 1. And so there's enough symmetry in the problem that they reduce this nonlinear PDE to a system of fully nonlinear ODEs. Right? It's still a system and it's still fully nonlinear, but they're ODEs, and miraculously these are almost always exactly solvable. So we have an explicit formula for the metric and the 3-form and everything. Now we can't expect that to happen in the compact case. Just like in the Calabi-Yau world, you can't expect an explicit Calabi-Yau metric on a compact manifold. It's really a sort of a transcendental problem. The best we can hope for is to prove that there exists one using analysis, but we're not expecting to be able to write it down. So I want to make a contrast between the non-compact and the compact situations. You can use the Bochner formula to show that a compact irreducible G2 manifold can't have any symmetry at all. And so if you're going to construct compact examples that are irreducible, you can't use symmetry methods. So it's going to be much more difficult. Okay, so let me talk about compact examples. Mark already told you a lot about this. These are all found so far. These are all found using gluing techniques. So the idea is you take two pieces that you understand reasonably well or better than what you're trying to build, and you attach them together. You identify some region of one with some region of the other to glue them together. And then on this smooth compact manifold you've constructed, you want to prove that there exists a torsion-free G2 structure on that thing using some analysis. And then because you know the topology, then you'll conclude that if you have a torsion-free G2 structure, then it's an irreducible G2 manifold. So this has been done now a few times. The first construction was by Dominic in '94. This is an analog of the Kummer construction. If you don't know what that is, don't worry about it. I guess Mark said this is 2003. He's probably more correct than I am, but it was in the early 2000s. Alexei Kovalev glued two asymptotically. Was it 2000?
2003 is when it appeared.
Yeah.
In print.
Okay.
Presumably.
Yeah. Okay, so then I'm using the right convention because I used to say 96 here. That's when it appeared in print, and Dominic corrected me and said 94. So Kovalev glued asymptotically cylindrical manifolds together after some kind of complicated twist, which Mark explained. And just this summer, Mark and Johannes and Tommaso, who's also here, and Alessio gave a vast generalization of this construction where they produced orders of magnitude more examples. And I have this thing which has been with Joyce, which has been in the work, well, it's been done, but it hasn't been written up for several years now, which is the third paper I want to talk about if I have time. So this is another gluing construction. It's a different flavor from the well, it's still a gluing construction. It's a different flavor from the second and third examples. We glue a family, a three-dimensional family of Iguchi-Hansen spaces. The only reason I want to talk about this, because really it's probably a bit too early to say too much about it, but it's because this construction often fails. But the nice thing about it is when it fails, it actually probably gives us something nicer. We still haven't convinced ourselves of that. So I want to tell you that you can possibly use this construction to make G2 conifolds. But I have to tell you what G2 conifolds are first. Okay, so keep in mind that this will come back in the end unless you slow me down considerably. Okay, so Mark alluded to this as well. All these compact constructions, they use a very general result of Joyce. It's basically saying that if you almost have torsion-free, then you can get torsion-free by perturbation. So a little more precisely than Mark said, but still not completely precisely, if you have a compact manifold with a G2 structure which is just closed, but not co-closed, and if the torsion is sufficiently small, you have to control the L14 norm of the torsion and some other estimates, then if that's the case, then Dominic showed you can actually perturb this 3-form to get an honest torsion-free G2 structure close to phi, and in fact, even in the same cohomology class. Okay? And the idea is he wants to stay in the same cohomology class, so he just adds an exact 3-form. And he shows that if this is sufficiently small, and if you have these estimates on the initial torsion, then phi tilde being torsion free, that means being parallel with respect to its metric, is equivalent to a nonlinear, second order nonlinear PDE on sigma. So this right-hand side has quadratic terms, but it depends only on sigma and d sigma. And then he shows that you can get a existence of a solution by iteration procedure. Okay. And these constructions, now we have tens of thousands of examples, but we're probably still only finding a very small part of the landscape of G2 manifolds. Okay. I want to say something about the moduli space of compact G2 manifolds, because the aim of the project, the paper with Jason, is to study the moduli space question for G2 conifolds. So I have to tell you what happens in the classical case first, in the compact case. Okay, so suppose you have a G2 manifold. This slide doesn't need irreducibility, but you might as well just assume irreducible, but it needs compactness. So you have a compact G2 manifold. Then you can look at the space of all the torsion-free G2 structures on the same underlying smooth manifold, modulo diffeomorphisms isotopic to the identity. Right? Diffeomorphisms will preserve the condition of being torsion-free. So this is some topological space. Usually moduli space questions, especially in complex geometry, have obstructions. But here it's as nice as can be. The moduli space is a smooth manifold, finite dimensional smooth manifold. And in fact, it's locally diffeomorphic to an open subset of the third cohomology of the manifold, the 7 manifold. Right? So in fact, the map is, if you take a a torsion-free G2 structure on M, an equivalence class of those modulo diffeomorphisms, and you map it to the cohomology class, because any representative is a closed 3 form, and pullback by diffeomorphisms preserves the cohomology class. So if you map it to its cohomology class, this is a local diffeomorphism. Okay, so the important thing about this theorem is that the deformation theory of compact G2 manifolds is unobstructed. And the infinitesimal deformations have a topological interpretation. So the tangent space to M at a particular equivalence class is naturally identified with the harmonic 3 forms, harmonic with respect to the metric at that point on the moduli space. Okay? Again, I'm emphasizing this because when I show you the answer for conifolds, well, first of all, it won't always be unobstructed. There will sometimes be obstructions. But then the infinitesimal deformations will have a topological component and another component, which is analytic. Okay, I want to tell you what goes into the proof, because when we do this for conifolds, we try to follow Dominic's approach, but we have to modify things in several places. So the proof has 3 basic ingredients: the implicit function theorem for Banach spaces, and this is fine whether M is compact or not, and then some Fredholm theory of elliptic operators and some Hodge theory, and definitely 2 and 3, especially, well, both of them, require the compactness of M. So our G2 conifolds will be non-compact with some extra data. So in particular, we can't just use 2 and 3 in this form. We have to modify them in some way. Okay. So I'm blazing through there, but that's good, because this was supposed to be the review. I'm going to slow down. So I want to tell you what G2 conifolds are, give you the definitions, say something about examples, and then I'm going to tell you our result, which is about the deformation theory of these things. So there's 2 kinds. For us, there's 2 kinds of G2 conifolds for Jason and I. There's the ones that are asymptotically conical. I'll give you the definition in a few minutes. And then there's the ones with conical singularities. And you can be more general. You can allow both at the same time. And Tommaso does that frequently. But we just chose not to do it. I'll tell you why we chose not to do it, but also, I mean, the main reason is to keep things a little simple. Okay, so before I can tell you what a conifold is, I have to tell you what a G2 cone is. So a G2 cone, well, it's going to be a Riemannian 7 manifold, which is topologically, it's an interval times a compact 6 manifold. This is a 6 manifold, such that there's a G2 structure, a torsion-free G2 structure on here, with induced metric coming from phi being the cone metric. This is a cone metric. So sigma is some compact Riemannian 6 manifold. And we want to have a metric on here such that when you take the cone over it, you get something with holonomy contained in G2. Okay? Now you can discover exactly what kind of a 6 manifold sigma has to be. Oh, I said I was going to change it up. You can discover exactly what kind of a 6 manifold sigma has to be in order for the cone over it to have holonomy G2, and this has been well known for a long time. This is what's called a strictly nearly Kähler 6 manifold. And some people are starting to call these gray manifolds because Alfred Gray worked a lot on them, and I think it's probably a good idea to use this name. So what is a gray manifold, or a nearly Kähler manifold? It's an almost Hermitian manifold, so it has an almost complex structure. This is not integrable. It's never integrable. Has a Riemannian metric. J is orthogonal with respect to G. So, and they determine a 1-1 form, omega. So this package is an almost Hermitian manifold. Every time you have an almost complex manifold, then the tangent bundle is a complex vector bundle. Of course, it's not holomorphic. There's no holomorphicity. Doesn't make sense here. But it's a complex vector bundle, so you can talk about its first Chern class. So the first Chern class of the tangent bundle is 0, which means there's a nowhere vanishing smooth 3-0 form, capital omega. Right? And little omega and capital omega are related by these equations. I mean, these constants, as long as you scale them the same way, are slightly arbitrary, but this is the one that gives us the nice formula here. Otherwise, it'd be an overall scaling thing here. So these are the strictly nearly Kähler 6 manifolds. So the cone over these gives you something with holonomy G2. Okay? So this is analogous to if you have, well, you may have heard that if you have a Sasaki-Einstein manifold, then the cone over that is Calabi-Yau, right? That is probably true. Okay, so these are going to be what's called the links. The link is this 6 manifold. The link of a G2 cone is a nearly Kähler 6 manifold. And there are only 3 known compact examples so far. I think there are several non-compact examples, but the only known compact examples so far are all homogeneous. And there's a theorem of Boutrouille that says these are the only homogeneous examples, these 3. Actually, there's also S6. I'm throwing away S6 because the cone over that is R7, which is not singular. I really want something to be singular. I want this metric to be singular as you approach R equals 0. So there are 3 known examples, but there are expected to exist many examples. This is from considerations in physics that these G2 conical singularities are important in the physics. But also, I mean, the only reason we haven't found any more is because the equations are too hard to solve if you don't impose some symmetry. I think there is a theorem that the cohomogeneity 1 compact do not exist. But there should be lots of examples with no symmetry at all.
Is it known that those 3 are the only homogeneous ones?
Those 3 are the only homogeneous ones. Yeah. Okay, so what is an asymptotically conical G2 manifold? I have some nice pictures. So those, waking up early on a Sunday morning has the advantage that you get to see some pretty pictures, even if you don't pay attention to the talk. So we have a n and phi n is an asymptotically conical G2 manifold of rate nu. Nu is some negative number, real number, asymptotic to the G2 cone C, phi c. So the data is you have a 7 manifold with a G2 structure, in fact, a torsion-free G2 structure, okay, and a particular cone at infinity and a particular rate. So the definition is, outside of some compact set, our 7 manifold, if you take away the compact set, is diffeomorphic to a neighborhood of infinity of the cone, right? And the 2 G2 structures, the 2 torsion-free G2 structures, if you look at their difference, then the derivatives of the difference decay at like r to the nu minus k as r goes to infinity for all k. So now it doesn't matter really which, you might as well take the cone metric here to take this Levi-Civita connection, but it really doesn't matter because with either one, this is the equivalent definition. So it says that the 2, 3 forms, as you go off to infinity, are approaching each other at rate nu, and the derivatives at rate, kth derivative at rate nu minus k. Okay, so, I mean, the first thing to say about this definition is that there's only one end, right? You can a priori ask for multiple ends, but because the holonomy is exactly G2, these things are irreducible. Actually, I should say, sorry, let me go back here. The G2 cone, I just said that it's a torsion-free G2 structure, and there's a theorem, I think, of Christian Baer that says if you have a cone with holonomy contained in G2, it's either R7, when it's not really a cone, it's smooth, and that has trivial holonomy, or the holonomy is exactly G2. So this phenomenon of having SU2 or SU3 in intermediate holonomies doesn't happen for cones. So because I really want them to be cones and have singularities, then it's going to always be irreducible. It's going to be full holonomy G2. And now our asymptotically conical thing, because it's approaching something which has full holonomy G2, it's easy to see that the holonomy can't get smaller. So this will always be irreducible. And then you might say, well, why don't we have multiple ends? Because the holonomy is full G2, if we had multiple ends, because it's a Ricci-flat manifold, if we had multiple ends, Shiger-Gromov splitting theorem would say we'd split off a factor, metrically split off a factor, a line, and then the holonomy would reduce. So there can only be one end. And that's because this is a complete metric, so we can use the Shiger-Gromov splitting theorem. So there are 3 known examples of asymptotically conical G2 manifolds. I mean, it's possible, I think, that the physicists have found more. I haven't kept up completely with those papers. But the Bryan-Salomon manifolds, which were actually independently discovered by Gibbons, Page, and Pope, are asymptotically conical. And these 2 examples have rate -4, and this one has rate -3. So that's going to be important. Well, actually, you probably won't see why it's important in this talk, but in the proof of our theorem, the analysis is extremely different depending on whether nu is above or below -7/2. And there are examples on both sides of that barrier, so we have to actually do the proof 2 different ways, essentially. There's my picture, my pretty picture of an asymptotic G2. It's I can't draw in 7 dimensions, and all my strange topology just looks like a bunch of holes. Okay, so the important thing you have to remember is there are 3 examples of these. Let me tell you now what a conically singular G2 manifold is. This is the other example of a G2 conifold. So we take a compact, there should be the word compact here, a compact topological space such that when you remove a finite number of points, it becomes a non-compact smooth manifold, 7 manifold, with a torsion-free G2 structure. So this non-compact part, we're going to call this a G2 manifold, conically singular CS G2 manifold of rate mu1 up to mu(n). Oh, I think my mu's become mu's later on, but anyway. mu1 up to mu(n), where these are now positive, asymptotic to the G2 cone Ci, phi Ci. If, again, outside of a compact set, the difference, the set theoretic difference, is just a disjoint union of a bunch of neighborhoods of the origins of those cones. And again, the G2 structure on M, if you compare it to the G2 structure on the ith cone and you take the kth derivatives, then this is order of Ri to the mu I minus k as Ri goes to 0, where Ri is the distance to this point xi. Okay? So it's the same thing, except now we can have lots of singularities. And the reason we can have lots of singularities now, even though, again, this is full holonomy G2, is because this metric is not complete. So we can't use the Shiger-Gromov splitting theorem to say there's only one end. And now if we wanted to allow these kinds of singularities and asymptotically conical ends, we can have lots of each of them, but we just didn't do that. Yeah.
So are these decaying to a point at infinity, or are they?
These are all, in here, these are all decaying. These are all going to a vertex of a cone.
And then in the previous picture,
There was only one, and it was going to the, not to the infinity. Okay, so let me say something about these conically singular G2 manifolds. So in the physics, this is what I've been told, the M theory needs these compact CS G2 manifolds, because apparently if the G2 manifold is smooth, then there can be no matter in the universe. And since we see matter or mass, they need conical singularities. Now, I still don't understand any of this, so please don't ask me about this sentence here. But let me say something.
It may also require other singularities.
It may also require, and so this is something that the mathematicians have been trying to figure out from the physicists. Are they asking for these singularities because this is what they want, or because this is the easiest thing so far? And when we give them the singularities, they may say, now we want more. Right? But let me say something about examples of these. There are no known examples. Okay, but that's not a reason to be deterred, because they're expected again to exist in abundance, and I will give you arguments convincing you why this is true, that there should be lots of these. Well, first of all, I'll show you why my result with Jason on the moduli space question, and another result I had 4 years earlier, gives you evidence that these should be there. But then if I do have time, I'll talk about my other work with Joyce, where we're trying to construct these. Okay, that's this part here. So the paper with the compact smooth G2 manifold should be ready next year. But unlike Dominic, I'm not confident enough to not put the question mark on my expected delivery dates. Okay, so why, I'm going to start to explain this why they're expected to exist. So these kinds of these are singular objects. They're not smooth manifolds, but we should expect them to arise as boundary points on the moduli space of compact smooth G2 manifolds. So if you, the moduli space is of course non-compact, and if you want to compactify it, you want to throw in things which are not going to be smooth manifolds. They're going to be singular objects which are going to be arising at some kind of limit of smooth compact G2 manifolds, right? So this is one way to possibly compactify the moduli space, or one thing you should have to throw in. It's probably not the only, almost certainly not the only thing. But why should they arise as boundary points? Well, one way to show that they should arise as boundary points, and this would give evidence that they likely exist, these G2 manifolds, CS G2 manifolds, is to show that if you did have one, even though we don't have any examples yet, if you did have one, you should always or often be able to desingularize this into a family, a one-parameter family of compact smooth G2 manifolds, which is converging to this conically singular object in some way. So if we could show this, then that would give evidence for their existence. One way to desingularize them is by gluing, is to cut out a neighborhood of each of those singular points and glue in something, in fact, an asymptotically conical G2 manifold, such as the Brown-Salomon examples. So in fact, this is what I did 4 years ago, or I guess I started 4 years ago, published in 2009. If you have, again, these don't exist yet, but if you had a conically singular G2 manifold with isolated conical singularities that are modeled on these cones, G2 cones, and suppose you had the objects that you want to glue in. You had the asymptotically conical G2 manifolds modeled on the same cones. So the picture is you have these singular points with some complicated topology, and you also have asymptotically conical things which at infinity are looking like the same G2 cones that these are looking like at the vertex. And you want to identify neighborhoods and do this gluing. So you're putting together torsion-free G2 structures. You're destroying the torsion freeness. You're introducing torsion on the annulus, and you want to perturb it using Dominic's theorem. So the condition you need is that the rates have to be no smaller than -4 for this theorem, and a certain necessary topological condition has to be satisfied.
Is that the right direction for your rate?
Yeah.
Faster than -4?
No, less than that. Yeah. Because I want to use -4 and -3. Yeah. Great.
Well, I mean, if something is very small, it's also got a low bound. Sorry, no, what am I saying?
The things, I need to have these things to put in, and these things.
-3.
Oh, thank you. Yeah, that's right. Because I wanted -2 and -4. Okay. See, this is why I told you I would send you my slides last night. I need this to be less than or equal to -3, because I remembered that it works exactly on the known examples, but there's a barrier exactly at the known examples, but it's not -4. It's less than or equal to -3, so I apologize for that. So if the rates are all less than or equal to -3, and there's a certain necessary condition that's satisfied, then you can always glue in these ends to get a compact smooth G2 manifold. And there's my nice picture here. The main reason to put this on is, well, I don't think that many people read this paper. And so I wanted to show this picture because it took me several days to create it. To a few more people, there's probably more people in this room than have read this paper so far. Okay, so this gluing, this desingularization can essentially always be done with the known examples. And so it's saying that if these things existed, they would, I didn't say it in this theorem here, but there is a one-parameter family of smooth things that converges in some sense to the conically singular thing. So these things would arise in the boundary point, on the boundary of the moduli space. Okay, so looking at this theorem tells you why you should be interested in knowing how the conically singular and the asymptotically conical things would deform. Because if you know how the asymptotically conical things deform, it tells you something about how many ways can we desingularize. How many different things can I attach at each of these points, right? If I can attach a particular asymptotically conical G2 manifold, and if there are other asymptotically conicals nearby it with the same asymptotic cone, then I can do this gluing in several ways. Right? So this tells you about how many ways it can be desingularized. And if you know something about the moduli space of CS G2 manifolds, this would tell you something about how much of the boundary of the compact smooth moduli space would consist of these things. Because I'm showing you that they should be on the boundary. And if we can show that if you have one, then it moves in a big family, then that might sweep out most of the boundary. So here's our definition of the conifold moduli space. So when I say G2 conifold, I mean either an asymptotically conical G2 manifold with one end, that's all it can have, or a CS G2 manifold with a finite number of ends. we don't mix the two together. And then we fix the rate here. If it's asymptotically conical, this is just one negative number. If it's conically singular, this is an n tuple of positive real numbers. Okay, so we define M nu to be the moduli space of all the possible torsion-free G2 structures on this same underlying manifold, asymptotic to the same G2 cones with the same rates. Right? We're fixing the cones at the ends, modulo the action of the diffeomorphisms that preserve this condition. And that's just the diffeomorphisms whose infinitesimally generating vector fields are rate nu plus 1 at each end, nu I plus 1 at each end. Okay, so that's our definition. That's some topological space. On the next slide, I'm going to give you the theorems. So I need some definitions. I alluded to this in my desingularization theorem. There's a natural map from the kth cohomology of M. This is the non-compact part, right? To the sum of the cohomologies of sigma I. So you can think about this nicely in terms of smooth forms. If I take a cohomology class in here, it's represented by some closed form. I just restrict the form to a neighborhood of each singular point. And there it's a closed form there as well. So, and the topology of the neighborhood of the singular points is just an interval times sigma I. So the cohomology is the same as the cohomology of sigma I. So you just project to those classes here. So these maps, upsilon k, are important. And also the other important thing is the space of homogeneous closed and co-closed 3 forms on each cone, on the cone Ci of rate lambda. I'm not going to define what it means to be homogeneous of rate lambda. You could probably guess, but I'm not going to need to show you the details here. So this is just some space of forms that are defined by some differential equation on the cone. So the theorem, I'm going to state the AC version and then the CS version, says that for generic rates, you have to avoid a finite set of critical rates. And I'll tell you why on the next slide. But except for a finite set of critical rates, we have the following. In the asymptotically conical case, as long as the rate is in this range and you avoid the critical rates, then the moduli space is smooth finite dimensional manifold. And the dimension is equal to this. It depends on the range. So it's mostly topological, but there could be some analytic contribution. So if you're between -4 and -3, it's just topological. It's the dimension of the compactly supported third cohomology. And then as you cross -3 turns out to be one of these critical rates that you have to avoid. And when you cross -3, but you stay away from the next critical rate, so epsilon is some small positive number that we can define precisely, then you add this extra topological bit. And then if you want to keep moving up to -5/2, you add these analytic deformations. Remember, these are, here there's only one end. So this is the space of closed and co-closed 3 forms on the asymptotic cone, which are homogeneous of order lambda. Turns out, so far, we can't go higher than -5/2 because of some use of integration by parts. We want to be in L2, and this looks like it's a barrier that we can't cross. But in certain cases, if you know something about the cone, we may be able to push this up all the way to 0. But for now, it definitely includes all the known examples. Remember, the 2 of the examples are rate -4, and -4 is critical. So you can't describe their deformations at rate -4. But if they're asymptotically conical of rate -4, then they're certainly asymptotically conical of rate -4 plus epsilon. And we know how they deform as asymptotically conical manifolds of that rate. Okay, so this is the nice situation where everything is smooth. In the AC case, if the rate is less than -4, you can, in general, probably get obstructions. But we can compute the virtual dimension or the expected dimension exactly. And so as the rate decreases below -4, it gets smaller than this. So we have to subtract rank of upsilon 4 and then subtract some analytic stuff if you go further. So this is just the expected dimension, but there's an obstruction space. And so it's unclear whether or not those obstructions actually prevent us from integrating infinitesimal deformations to actual deformations. I'll describe the obstructions on the next page after I do the CS theorem. So in the CS theorem, again, if you avoid a finite set of critical rates, in general, the CS moduli space is obstructed. This is just like this case here. And the dimension here is H3. That's not the compactly supported. That's H3 minus this topological bit. Together, these two together give you the image of the third compact, so H3CS in H3. There's a map from H3CS into H3. And this bit together is the dimension of the image of that, minus these analytic contributions. So you see it could be negative, right? This is an expected dimension. And in both cases, the CS and the AC, whenever there are possible obstructions, the obstruction space is easy to describe analytically. So you look at the space of forms on the cones at the ends. You look at forms which are of degree 2 plus 4, a 2 form plus a 4 form, which the sum of which is in the kernel of D plus D star, but whose individual pure degree components are not independently closed and co-closed. So of course on a compact manifold that can happen, because if something's in the kernel of D plus D star, then it's harmonic, and if it's harmonic, it's closed and co-closed by integration by parts. But here we can't always integrate by parts, so there can be things of a mixed degree for which the sum is closed and the sum is co-closed, but the pure degree parts are not. So this is exactly what's obstructing it. And the proof, we have to adapt those aspects of Dominic's proof to the non-compact setting. So we need to use the Lockhart-McCohen machinery of weighted Sobolev spaces and Fredholm theory. So Lockhart-McCohen have this theory, which other people have worked on too. I mean, I don't know the full literature here, but basically they adapt Fredholm theory results of elliptic operators to the non-compact setting as long as you use weighted Sobolev spaces. And the problem is that you get the results almost always, but there are some critical rates for which the theory fails, and you have to just avoid those rates. Plus, you have to develop some Hodge theory type results for these asymptotically conical or conically singular manifolds. And you have to throw in some ingredients into the mix which are specific to G2. So there's a Dirac operator here, and to prove our slice theorem in one of the cases, we have to prove that this Dirac operator is surjective, and we have to use the fact that using the Bachner formula and the irreducibility of the holonomy, that if you have an L2 harmonic one form, it's parallel. So there's various ingredients that go into here, and I can say more if you want to hear it. But let me talk about applications of this theorem. So we only have 3 known examples of these things, right? The Bryan-Salomon examples. And these are rigid. In fact, I'm actually lying to you here because there's something you can always do, which is kind of a dilation. You can always scale the G2 manifold, and if you do it in the right way, you scale the overall thing, and then you reparameterize the R coordinate infinity to get it asymptotic to the same cone. This is always a deformation, but this is kind of a trivial thing. So those are always there. But apart from that, there's no other deformations. So these things don't deform in any non-trivial way. And another application, which is not apparent from the statement of the theorem, but if you had a CS G2 manifold, and if you knew that all the singularities came from links only belonging to 2 of the 3 known examples, these are 2 of the 3 known examples of nearly Kähler 6 manifolds. This is not, there's a different, this is only diffeomorphic to CP3, right? It's a non-Kähler CP3, and this has a different metric. It's not the product metric. So if all the links come from these 2 examples, then it turns out all the obstructions vanish, and the CS moduli space is smooth. Nice. Okay. And this will also be true even if we throw in the other known example into our singularities, as long as we know that this has no strictly nearly Kähler deformations. So there's some work by Moriano and Semmelmann that show that these are rigid as nearly Kählers. And this one may or may not be rigid. They compute the infinitesimal deformations, and it's non-zero, but we don't know if those actually integrate to honest deformations. So if one can answer that question, if this doesn't deform as nearly Kähler, then with any of these links, we would have a smooth CS moduli space. And when this is true, when the CS moduli space is smooth, because we're assuming that the links all come from here or here, then it turns out you can compute the dimension from our formula, and it's exactly 1 less than the dimension of the moduli space of the compact smooth desingularizations. So remember, I had the theorem that said, if you had, it's already here, if you had the CS thing, you can attach AC things to make it compact and smooth. Well, since it's compact, you can compute the dimension of the moduli space from Dominic's result. It's just B3 of the compact thing. And from our result, when the CS moduli is smooth, you can compute the dimension of that. And it turns out that the dimension of the CS things is exactly 1 less than the desingularized moduli. So it says that the CS singularities are the highest dimensional stratum of the boundary. In other words, most of the ways that this G2 manifold can become singulars to develop these CS singularities.
Sorry, Spiro.
Yeah.
So is that the only way you know of removing the obstruction? It's just by assuming rigidity?
No. Let's wait for.
Is that the analog of the stability?
No. Let me show you number 4. So statements 2 and 3 will be true in general for any CS if certain conjectures about the Laplacian on forms for strictly nearly Kähler 6 manifolds are true. So we can write down certain statements about eigenforms of the Laplacian on 2 forms and 3 forms for compact nearly Kähler 6 manifolds, which are true for these cases, right? So if those are true for all nearly Kählers and there's no deformations, right, that's included in these conjectures, then this would work in general. Am I right?
Yeah, but it is stability.
Okay.
But you do give sort of an abstract definition of stability index for.
Nobody knows how nearly Kählers deform yet, right? Non-infinitesimally. Okay, so I have 12 minutes, right? I want to tell you about this paper by with myself and Dominic that should appear next year, which is a new construction of compact G2 manifolds. And the reason it fits into the theme of this talk is that when this construction fails, which turns out to be frequently, it actually may be producing the first examples of CS G2 manifolds. So that's why it really fits in. It's not going to look like it fits in. I don't have enough time to go through all of that, so I'm gonna be quick. But you can always ask me after. And there's some even prettier pictures here. So this is a 5-step process. So I'm going to try to go through the steps reasonably quickly. So we start with a compact Calabi-Yau 6 manifold, or 3-fold, complex dimension 3, that has an anti-holomorphic isometric involution, right? So it's an isometry, anti-holomorphic, and it squares to the identity. There's lots of these, right? So if you take a quintic in CP4 with real coefficients, complex conjugation gives you one of this. And we take the product with a circle, and then there's a G2 structure, a torsion-free G2 structure on this product. And of course, it's not irreducible. It has holonomy SU3. But what we can do is we can produce an involution on the 7 manifold by taking the involution we've started with on the Calabi-Yau and just reflecting the circle. Right? And then sigma is an involution that preserves the G2 structure because it takes omega to omega bar, so the real part doesn't change. And it flips theta and omega, so this doesn't change. Okay? And then we take the quotient, m mod the action of this involution, and we get a G2 orbifold. So it's a non-singular object, and the singularities are actually a 3-dimensional family, and they're locally of the form R3 times C2 over plus or minus 1. Okay? In fact, the singular set, it's easy to check, is 2 copies of a special Lagrangian in the Calabi-Yau in N. So A is the fixed point set of tau. So it's a compact special Lagrangian. It's also totally geodesic. This is actually important in some of the computations that we do, but you won't see it here. So it's a totally geodesic compact special Lagrangian, 2 of them in there. So what we want to do is from this orbifold, we want to somehow remove the bad part and glue in something nice and smooth and get a new compact smooth G2 manifold. So we want to cut out the locus, a neighborhood of the singular locus, and glue in something non-compact and smooth to get something smooth and compact, and hopefully we'll have a closed G2 structure with small enough torsion so we can just invoke Dominic's theorem, like all these constructions do. Okay? L is compact, so we use the normal neighborhood theorem that says that a neighborhood of L in M is diffeomorphic to a neighborhood in the 0 section in the normal bundle. There's my fancy graphics here, more high-tech than before. So this is the exponential map. So we're identifying a neighborhood of L in M with a neighborhood of the 0 section in the normal bundle. And it turns out, well, we know this has already been discussed by Conan and others, that L is actually associative. And if you have an associative submanifold of a G2 manifold, if you choose a non-vanishing 1 form or a non-vanishing vector field equivalently on the submanifold, then cross product with that vector field on the normal vectors actually turns out to be a complex structure on the normal space. I'm not saying can't be integrable. It's just a complex vector bundle. So the normal bundle, once you choose alpha, is a rank 2 complex vector bundle over this 3 manifold. And actually, the diffeomorphism on the previous page here descends to the quotient of m by the action near the singular point. Right? So there's my picture. This is the orbifold, and this is the normal bundle where I've quotiented each fiber by plus or minus 1. So this is a fiber bundle with fibers C2 over plus or minus 1, and near the pink L, these are diffeomorphic. Okay? The fibers are C2 over plus or minus 1. So we want to resolve this P. This is a bundle over the associative whose fibers are of this form. Oops. So we want to blow up at the origin and do a fiber-wise blow up, replace each fiber by, the blow up of this is topologically T star of S2. Okay? And it turns out that this space, T star of S2, is well known. It has a holonomy SU2 metric, the Gucci-Hansen metric. In fact, it has a whole S2 times 0 infinity family of these metrics. So the S2 is a choice of complex structure on R4, and this is a scaling. Okay? Now, if this normal bundle was trivial, which it will not be in general, and if the special Lagrangian was a torus, which it will not be in general, then it turns out we can just choose any Gucci-Hansen metric on T star of S2, and our resolution, P tilde, would have a torsion-free G2 structure, because we can take one at a point and it'll be constant, just move it around. But this is not going to happen, because the L will not be a torus usually, and the normal bundle will not be trivial. So there is no canonical torsion-free G2 structure on the resolution. So we want to glue in the resolution is what we're going to attach a neighborhood of the origin of the zero section in the resolution is what we're going to attach to a neighborhood at infinity of the orbifold to get our smooth thing. But we don't have a torsion-free G2 structure on the thing we're going to attach. Okay? But actually, if you look at the moduli of Iguchi-Hansens, they're R3 minus 0. So this choice of alpha, this non-vanishing one form on the associative, on the special Lagrangian, is telling us really which Iguchi-Hansen metric to pick over each fiber, right? So alpha is what makes the normal bundle into a complex vector bundle, but it also tells you which Iguchi-Hansen metric to take. And so you could construct a canonical G2 structure using alpha. Once you've chosen alpha, you can construct a canonical G2 structure on P tilde, but it's not going to be torsion-free. And if you look at the estimates that Joyce has in his theorem for how small the torsion has to be, there's no hope for this to work unless alpha is closed and co-closed. So we have a non-vanishing harmonic one form on this special Lagrangian, compact special Lagrangian. So that's very hard to ensure, right? But let's assume for now that we did have a nowhere vanishing harmonic one form, right? Then we can actually do the gluing. So this is what I've been saying. So you take a neighborhood, you take an annulus and an orbifold far away from L, but not too far away, and you identify that with a neighborhood of an annulus in the normal bundle over plus or minus 1, and then we identify closer still with another annulus. This is the resolution. So this is a T star of S2 bundle over L. So the green parts are identified by the resolution map, because away from the singular locus, or away from what is called the exceptional divisor, the resolution is diffeomorphism, and here we have diffeomorphism, so those get attached. And there is a canonical G2 structure on the middle piece. I'm not going to explain this. You basically expand in a power series to the distance to the origin, and you can get a canonical G2 structure here. So we have our torsion-free G2 structure here. The problem is that this one is an orbifold, so we got to cut away a neighborhood of L. We have a G2 structure here, canonical in some sense, but actually it's not torsion-free. And we have one here too, which is not torsion-free, and it wouldn't have a chance of even being small enough torsion if alpha wasn't harmonic. So we want to construct a closed 3 form on the total resolution here by interpolating between these G2 structures using here. And we compare the torsions we just fixed the metric on the middle piece. We have 3 pieces that are getting glued together. Sorry, I'm rushing a bit because I want to get to the punchline. It turns out these G2 structures are not closed, so you have to slightly modify them to get closed versions. That's easy to do. But more significantly is what I said, is that the torsion is always too big, even when alpha is a harmonic one form, which is a strong assumption. It's still too big, the torsion, to apply Dominic's theorem. So this doesn't happen in the other constructions because you're starting out with things that have torsion-free G2 structures. You still have those complicated matching conditions. So the difficulty in other constructions lies in the algebraic geometry. Here, the difficulty, there's very little, there's almost no algebraic geometry. Here, the difficulty here is in killing this torsion. So the problem is that this bundle of Gucci-Hansen spaces doesn't have a natural torsion-free G2 structure. And there's this intermediary manifold, and even on this intermediary piece, the one in the middle, the torsion there is still a bit big. So you have to do 2 corrections, and I'm going to, whiz through these because you can see them on the website because I'm out of time. But there's one thing you can do is, the problem is we made the wrong identification of a neighborhood of L with a neighborhood of L in M hat with a neighborhood of the zero section in the quotient of the normal bundle. It wasn't the right identification to make. And if you change the connection to change what it means to be vertical, and if you, what it means to be horizontal, and if you change it, you precompose by some other diffeomorphism so you can bend the vertical. If you do this the right way, it turns out you can make the torsion here small enough. So this is just kind of an artificial problem. It just means we weren't doing the identification in the right way. The real problem is modifying the torsion on p tilde. Right? So here you actually have to do some analysis to introduce a correction term, to change the G2 structure that we put here, the natural one, to make the torsion small enough. You have to solve an elliptic PD of this form, d plus d star of some mixed degree form on the Gucci-Hansen space. It's some given form which comes from the original G2 structure. So it's a linear elliptic PDE on a non-compact manifold with nice behavior at infinity. And it turns out you can solve this equation, so you can do this correction. And so you can get the construction. So let me make some remarks in the last 2 minutes. The construction is actually a bit more general. You don't have to start with a Calabi-Yau with an anti-holomorphic involution. You can just start with any G2 manifold that has an involution that preserves the G2 structure. Then the fixed point set is associative and everything is the same. The only reason I formulated it at the beginning in terms of a Calabi-Yau is because then you can actually get examples, right? There are no known examples of compact G2s with such an involution. So this is why we do this, and you can construct. We haven't counted how many we're getting, like Mark's team did. So this is still the enumeration of how many we're getting is still to be done, if we can actually enumerate them. But this is the major problem, right? We can't guarantee that L will admit a nowhere vanishing harmonic one form. The problem is that the metric on L is induced from a Calabi-Yau metric on N, which we don't know. Remember, on a compact manifold, we can't write down the Calabi-Yau metric explicitly, so we don't know the induced metric on L explicitly, so it's impossible really to tell that the harmonic one form will be nowhere vanishing. But using mirror symmetry arguments, if you're near the large complex structure limit of the Calabi-Yau moduli space, you can expect it to contain you can expect the Calabi-Yau will contain a special Lagrangian torus that's almost flat. So there will be examples where you could guarantee this, but generically you can't. Generically, a harmonic one form on L will have isolated zeros, right? And when that's the case, at those isolated zeros of the harmonic one form, we can't do our gluing. We don't know what a Gucci-Hansen space to put in, right? They're really converging to the singular model C2 over plus or minus 1. Okay, so what we're doing is we're resolving M to M tilde except for a finite number of singular points. We've got something which is compact. It's not quite smooth, but there's only a finite number of points where it fails to be smooth instead of a three-dimensional family. And in fact, near the singular points, you can sort of do a back of the envelope calculation to show that the manifold topologically looks like a cone over CP3. And that's good because there is a G2 cone whose link is CP3, one of the Bride-Salomon manifolds. This is not right. There is a cone. There is a nearly Kähler 6 manifold with link CP3. And one of the Bride-Salomon manifolds is asymptotic to it. So what we'd love to do is to show that in this case where our construction is failing, which is frequently, we're actually going to be able to get CS G2 manifolds. Right? So we're almost there. We've got something which has a G2 structure with small torsion when we do this correction, but the problem is that the torsion is not small enough near the singularities. We have to do another gluing. We have to change the G2 structure. Maybe not gluing is the wrong word. We have to change the G2 structure again near those singular points to make it look like the Bride-Salomon G2 cones over CP3. So we need to do enough further perturbation. To do this, you need to get a version of Joyce's existence theorem for CS manifolds. This is probably not hard. The part that Dominic thinks is too hard, and I'm luckily too naive to believe him, so I'm going to try it, is to understand how the Iguchi-Hansen metric is analytically related to the G2 cone. This one, as the Iguchi-Hansen parameter goes to 0. So if you can perturb again, if you can change the G2 structure again to make it look like this one, then there's a hope of getting something with a G2 structure, a CS manifold with a G2 structure with small enough torsion, and then you can get a version of Dominic's theorem like this to make it work. If we can do this, this would be the first CS examples. And then if this works and you can produce CS G2 manifolds, you give them to the physicists because that's what they really want. But then you can desingularize further with my theorem from 4 years ago to actually get a G2 manifold. So it would be a two-step process, right? The first step is the hard step, which gives you hopefully a CS thing. And then going from the CS to the smooth one by desingularizing the cones, we know we can do that. So that's still in progress, and hopefully in a year or two. Before your 80th, I can definitely report on this. So that's all I wanted to say. Thanks.
Any questions?
Yeah.
We're considering isolated point singularities. And along the way, you considered three-dimensional singular axes, I guess. But is it worth considering things with conical singularities along other dimensional submaterials?
So the ones I was showing you in the third part of the talk, the orbifold singularities, those were not conical. You can show that. Is that right? That's right. What's the statement? Orbifold singularities in the G2 world can't be conical. They can in the Calabi-Yau world, but these are not conical. So I think if you had so orbifolds are out for conical. But if you wanted to have a family of singularities that kind of looked like a cone times an interval, I think probably the holonomy would reduce then. I have to think about it. I mean, certainly if it was smooth and that was going on, the holonomy would reduce. But probably also if you had like a picture that looked like this, right? And it had holonomy contained in G2, I think it probably would be SU3. So that puts you into a similar. I don't want to call Calabi-Yau threefolds a simpler situation, but I just did. So
I don't think
that's not true.
I think if you look at the kind of examples that we're constructing, then so you start with, say, something like a smooth pattern, and say let's just take a quarter, and then build your asymptotically symmetrical Calabi-Yau out of that. But then you could allow your quartic to degenerate to something with nodes, and then again, you might hope that that would emit a metric with conical singular things, which we still don't know.
Which wouldn't be isolated.
So, we're talking about just the Calabi-Yau. So, then if that emitted this, then you could try and match a pair of those. And then on the other side, you could take a resolution of that and have a weak pattern. And so in the middle, there should be things that look like this.
And they would be all on G2.
So they should be on G2.
Okay.
But I mean, we still don't know they exist because. But I guess.
Okay, so then I'll revise my answer and saying isolated is the first step. Yeah, and this seems to be what the physicists are asking for, but it's unclear to us. It's unclear to us if that's because that's really what they want, or because they're asking for the first step.
Well, I was going to ask, but maybe you just answered it. You have some candidates for the top stratum in the boundary of the moduli space.
Yeah.
I wondered if you had candidates
for what?
straight further down.
Yeah, no, we don't. So there probably are more complicated things that can happen. I guess that would be further down, but we haven't thought about that.
The harmonic one forms you've been talking about.
Yeah.
So that corresponds to a deformation of the spatial Lagrangian. Is there a geometric interpretation of why?
Good question.
I mean, maybe you think harmonic one forms where it's non-zero for analytic reasons. But maybe there's a geometric interpretation of forming a special Lagrangian that
That's a very good question. So this is telling us exactly that there's, for this alpha, because the moduli space of special Lagrangian deformations in the compact case is harmonic one forms, and it's smooth. So yeah, for this alpha, we get a family of special Lagrangians. I never thought about that. That's intriguing. I mean, really, it's telling us which Iguchi-Hansen to glue in. But you're right. If it's also telling us how the special Lagrangian can deform, then there might be some more geometric insight to be gained from that. We could talk about it.
I'm just wondering if there are some interesting geometric structures on your modular spaces.
Yes, absolutely. So in the modular space of compact G2 manifolds is what's called an affine Hessian manifold. So if you take tangent bundle of that, it's scalar. Actually, there's a natural metric, which is there are different ways to put metrics on there. And one of the ways to do it, the tangent bundle turns out to be honestly scalar. Another way turns out to be kind of a Lorentzian Kähler. There's a complex light-like direction, and then there's space-like directions. And so there is some additional structure on that moduli space. There's also a cubic three-form called the Yukawa coupling coming from physics. And it turns out that the Yukawa coupling, it's a symmetric cubic tensor, and it's really the third derivatives of this, what's now called the Hitchin superpotential, which is the function whose Hessian gives you the metric on the moduli space. So there's a lot of structure on the compact G2 moduli space. Probably there are analogs of this in the CS or AC G2 moduli, but we haven't looked at that yet. Again, the non-compactness makes it a little...
So the modular space itself is non-compact, yes?
It's non-compact. When I say compact moduli space, I mean the moduli of compact stuff.
So when you compactify the modular space, what happens with this structure?
Well, we haven't actually, we don't know. Nobody's compactified the moduli space yet. Yeah. So it would be nice to see exactly what happens at the boundary to these structures. Like, does the Yukawa coupling blow up at some rate? And the curvature. That we haven't done that. Those are plans for the future.
The Giga Colding Tian Kähler machinery. The special boson case.
Yeah, well, that tells you things about like the metric and the curvature and things like that. But all this additional structure is sort of particular to. There are this kind of additional structure I've been mentioning is similar in the Calabi-Yau case. Those are special Kähler, and possibly people have studied what happens to the special Kähler structure at the boundary. I don't know if they have. So we'd have to see that first before trying to do it here.